Hi, and welcome to part 2 of this video where we are designing pearl necklaces, or a different way of saying it, we're just populating a curve with a bunch of spheres with some particular rules. In this one, as we did before, we have implemented an algorithm where we can control how many spheres do we populate over the curve with an exact number, but we have the problem that because of the algorithm that we're using, we know that the pearls fill all the curve all the way till the end, but in some areas where the angle is very concave, these pearls overlap a little bit. So we've also implemented another version where we can control the diameter of those spheres, and we can control the fact that they are perfectly tangent to each other. However, we have the problem that there is a little bit of leftover here at the curve, but we will figure out how to combine all those constraints in the next video, where we're going to do a little bit of iterative optimization on this algorithm. In this video, we're implementing these two rules. We're doing those in native C# components, so we're going to be using Rhino Common and C# scripting. So this is a beginner level, so I'm going to explain everything very carefully. And but if you're interested in learning how to move from Grasshopper to C# scripting within Grasshopper, this will be a very useful video for you. Okay, so let's get to it. Okay, but before we write any code, let's do a quick refresher of what we did in last video. You should check the last video for the full tutorial, but anyway, the basics of the algorithm that we're going to implement is that if we have a curve that we want to populate with spheres representing those pearls, then what we're going to do is, first of all, we're going to subdivide that curve into an amount of points equal to the spheres that we want to populate. And then we need to figure out the radius of each one of those spheres. The rule is going to be very simple. We're going to find the length of that curve. We're going to divide it by the number of pearls that we have minus 1, because if we have 3 pearls, we need to divide the length of the curve in 2 segments, the 2 segments that exist between the 3 pearls. And then we're going to multiply that by 0.5 or divide it by 2, because that distance would be the diameter, and what we need is going to be the radius. So that's the process that we're going to do. And in this video, as opposed to the previous one, we're going to write all of that in C# using Rhino Common and using Rhino Common to perform these operations. So let's take a look at how that could be implemented. All right. For those of you who are not perhaps very familiar with C# scripting inside of Rhino, I'm going to go a little slow on this one. So the way we do C# scripting inside of Grasshopper is we go to the Math tab, and here where it says Script, we can drop a C# script component. And this component is a component that, as we double click, we can customize the code that runs inside of this component. And we can use Rhino Common, which is the library that comes with Rhino, that has like a lot of very useful and powerful geometry operations, which are actually all the functions and all the operations that run inside of all the rest of the native Grasshopper components. So I'm going to drop it here, and I'm going to customize the inputs. So what I'm going to do is I'm going to zoom in, and I'm going to right click where it says X, and I'm going to change this to, for example, curve. Okay. So I'm going to change the names, and this one is going to be, for example, N, which is going to represent the number of pearls. And the other thing that is very important is that I need to right click on the input and make sure that the type of the input, the type of the object that is coming in, is the right one. So for example, for a curve, it should be here under geometry, it should be an object of the type curve. And for N, it needs to be a number with no decimal part. So in programming languages, that is usually referred to as an integer. So that's here, int. And then now I can just plug in here the curve. I can plug in the number of pearls. And as I double click here, you can see that this panel opens. And this panel contains a main function that is now taking in a curve object, and is taking in an integer, and is spitting out A, which is going to be the result of our operation. So for example, the spheres, right? I may actually want to rename that as well, and I'm going to call that spheres. So that now when I double click here, I can see that the output is going to be this reference object called sphere. And at this point, I am now ready to start writing my C# code inside of this component. So let's do that. And let's do that in two parts. First, let's find all the points along that curve. And the second one is going to be let's populate those points with the spheres. The first thing we're going to do is we're going to find the center points for the spheres, and we're going to do that by dividing the curve into equal length segments. If we go to, in Rhino Common, if we go to curve, to the curve class, we can see that this curve has a lot of methods, a lot of them being dividing by a bunch of different parameters. And we can see here that when it says divide by count, what we get is that we can divide the curve into a number of equal length segments. But we have two different versions. We have one that just takes a number and that takes a boolean, and another one that takes an additional array of points. What is the difference between them? The difference is that if we just use, for example, the first version that just takes the amount of segments and whether if we want to include the ends or not, the return type is going to be an array of doubles, which represent the parameters along the line or the curve at which those points are found. So this is what we can see here. And then we would need to perform a second operation where for each one of those parameters, we look at the curve and we find the point at that parameter, which is also a very simple operation that can be done. Somebody thought that if you were dividing by count, very often you also wanted not just the parameter, but you wanted the point. So they created a second overload where it's the same concept, it's the same function. You can still divide by count, amount of segments, include the ends, and it still returns the parameters where along those lines, along that curve, these centers are. But additionally, you can pass in, as a reference, you can pass in an empty array of points so that the function already gives you as well the actual points along that curve. Which means that in our case, because we don't really care about the parameter, we're not going to reuse that anywhere, this function is going to be much more useful for us because ultimately what we want is those points. So that's the one that I'm going to use here. So first of all, we need to make sure that we have all the parameters ready to go before we call the function. So we need to figure out how many segments we're going to divide in, and we need to create an empty array to be populated. So for example, I'm going to say here segment, I'm going to create a new variable called segment count, and this is going to be equal to the amount of pearls, so that's n, minus 1. Because remember, if we have a curve and we want to place 3 spheres, then we need to subdivide that curve into 2 segments. That's the amount of segments between those spheres. So it's always the amount of spheres minus 1. And also, I want to create a new point3D empty array that I'm going to call, for example, centers. And that is just going to start empty, because what I want is the function to populate that array with all those points. So now, to the curve that was passed as an input, I'm going to say, can I divide by count? And you can see here that there are 2 overloads. So I don't know why I'm not seeing the overloads, why they're disappearing, but anyway, so they are the ones that we saw before on the reference. So this is going to be segment count, then whether if I want the endpoints or not, I want them. And then here I'm going to pass in centers so that I can get all those points. I'm going to run this. I have an error. If I can plug in a panel here. And the error is going to be that argument 3 must be passed with the out keyword. I forgot to write here out so that this is not an input, but it's an actual reference to that object. And then if I run this code now, it's probably good. Just to verify that this is working correctly, I'm going to add here a dummy output, for example, A, and I'm going to output all those center points on the dummy output, so center, so that I can see them, centers, there you go, so that I can see them on the screen. Okay, I don't really need to output them, but Actually, why not? I could also design my component to output those centers. So yeah, so I'm going to do that permanently. So I'm going to rename this to cents, for example, cents, and then here I'm going to say centers is going to be equal to cent, and I'm going to create a new output here that I'm going to call centers. And as I run this, this has not updated. I think I should rerun it. The name centers do not exist in the centers. Yes, all right. So now it updated. Okay, cool. So we have the center points now, and then the next thing that we need to do is we need to figure out the radius and then create spheres on top of that with those radius. So let's give that a try. Okay, the way we're going to do that is we're going to first calculate the length of the curve, and we're going to divide that by the amount of segments that we already computed here. But how are we going to calculate the length of this curve? Well, we're going to use Rhino Commons methods to find that curve, because like doing it manually is pretty tedious actually. So if we scroll all the way down here, we can see that curves do have this method called getLength that give us return this double value, which is the length of a curve, or 0 if we couldn't figure it out for whatever reason. So let's say here we're going to create a double value that we're going to call length, and this is going to be equal to curve.getLength and open and close parentheses. We don't really need any argument here. If we just want to make sure that this makes sense, let's print something like, for example, length. Let's print this to the output here of the component. So as I run this, we can see that the length of this curve is 1.115 blah blah blah. And then what we can do here is we can create another variable called segment length, and this is going to be equal to the length of the curve. Actually, let's be a little more verbose. Curve length, so that we don't confuse things. This is usually good practice. What we're going to do is segment length is going to be equal to curve length divided by segment count. We could also print that here. We don't really need to. And then now what we will need to do is we will need to say sphere radius is going to be equal to segment length divided by 2. Or usually I like multiplying things by 0.5 so that I remember not to run into integer division problems. So that's the sphere of the radius of the sphere. Shall we print this out? Well, let's give it a try. So sphere radius, sphere radius, what does this look like? It looks like 4.13. I have no idea if that's a good or a bad value, but we're probably going to see as soon as we create the spheres, all right? And so the next thing is create spheres on centers. And how are we going to do this? Well, we're probably going to implement something where we create an empty array, and for as many points as we have, we create spheres with that radii. So what do we need to create a sphere? So if I say sphere s equal new sphere, what parameters do I need? I need the center and I need a radius. So those I already have. So let's create an array of spheres. For example, I'm going to call it S, no, I'm going to call it SPH, and this is going to be a new array of spheres with an amount that is going to be equal to how many centers do we have here. So we're creating an empty array, and we're populating it. We're reserving however many slots we need here given the amount of centers. And then with a for loop, I'm going to say int I is less than 0, I is equal to the length of their centers array and I++. What I'm going to do is I'm going to create a sphere S that is going to be equal to a new sphere with the center being each one of the centers, so sense I, and then the radius be the value that I calculated before. So that's going to be sphere radius. And then what I'm going to do is I'm going to place that sphere that I just created in the new array SPH. So the element in position I in this array is going to be equal to that new sphere that I just created. And now the outputs are going to be those centers, and the spheres are going to be SPH. And as I run this code, I got a typo there. This has to be spheres. And then as I do that, it looks like we have all those spheres nicely distributed along the curve. Okay, and I think that's pretty much it for this algorithm. I think this should be enough. Yeah, that should probably be enough. Okay, and the second part of the algorithm, the one where we control the radius of the spheres, is going to be actually easier. I actually thought it was going to be more difficult, but Rafael in the chat just pointed me to a function that is going to make things much easier. So what I'm going to do is, first of all, I'm going to deactivate the preview on this one, and I'm going to copy and paste here. I'm going to do a couple changes. So first of all, I'm going to create a slider here that is going to be the diameter. So this is going to be D, so I'm going to change that name. This is going to be the diameter of the sphere. And then here, I'm going to maintain the two outputs, the center and the spheres. But I'm going to remove a couple things here. Also, I forgot to do something. You see, the input, it's still an integer and it needs to be a double. So I'm going to right click here and say this is a double. So I'm going to follow the same principle. First, I'm going to find the center points for the spheres, and then I'm going to create spheres on those centers. So, but before we needed to compute the sphere radius, now it's just going to be as easy as using the value of D. So just so that I can reuse this code here, I'm going to create a variable called sphere radius, and I'm going to give it the value of D. Okay? Just for the sake of reusing this code without changing it. I could also just, actually, I probably just want to replace this with, sorry. No, actually, this is going to be D point, so 0.5 times D, or D divided by 2. So that's one thing. The other thing is that now I need to find the centers of these, the centers where the spheres are going to be. But remember, as per the previous video, now what we want is to make sure that all the spheres are perfectly tangent to each other. They only touch in one point. And then, therefore, the subdivision method that we need to use is a different one. Curves also have this other method called divide equidistance. That was the one that I was offered by Rafael in the chat. I was actually going to do this manually. But this one gives us 3D points on a curve that have where the linear distance between those points is equal. So what we can do now is, and it's just as simple as calling divide equidistance. What is the distance? So that's going to be the diameter. And then it gives us in return an array of 3D points. So very easy. I'm just going to create an array of 3D points. And I'm going to call it sense, as I did before. And then this is going to be equal to the result of the operation of, from the curve, calculating the divide equidistant, and here feeding in the diameter, so the value of D. And then as I do that, this should be now as easy as, well, I'm going to turn on the visualization, and now you can see that all these spheres are perfectly tangent to each other, right? We still have the leftover here. I'm going to, you see how as I reduce the radius, more pearls start popping out as soon as there's room on them. So, yep. So, all right. So we got the algorithm ready, and that's probably it. First, we have subdivided by the amount of spheres that we want, and then we have also created the algorithm where we subdivide given the diameter, and we make sure that they're perfectly tangent to each other. This works in 3D as well. And I think that's it for this video. In the next one, what I'm going to do is I'm going to combine these two constraints. So I'm going to create an algorithm where I'm going to use as parameter the amount of spheres, and I'm going to use generative optimization to make sure that I can find what the optimal radius for these spheres is, so that we have as little leftover curve as possible, so that the spheres fit their curve as best as possible. Okay, so if you like what you see, just click subscribe, etc., and then follow up on the third part of this video. Thank you.